identify the compound with molecular formula C10H10O from its NMR C13 depth COSY HSQC spectra. Show all key correlations that support your structural assignment. So here in this problem, we have been given the most valuable information to begin with, which is the molecular formula. So using the molecular formula, let's apply the degrees of unsaturation formula to find how many degrees of unsaturation this compound has. So the formula for degrees of unsaturation is 2C plus 2 plus hydrogen minus X divided by 2. So that's going to be equivalent to, there are 10 carbons, so that's going to be 20, plus 2, there are no nitrogens, so that's 0. There are no halogens as well, but there are 10 hydrogens, and this is going to be 0. And this is going to be 0. Divided by 2, that's going to be 22 minus 10 divided by 2. That's 12 divided by 2, which is going to be 6. So this compound has a total of 6 degrees of unsaturation. And it could mean like there may be double bonds, triple bonds, aromatic ring structures, and a combination of all of these. Next, let's go take a look into the NMR spectrum. So this section right here is the aliphatic region, and this section right here is the aromatic region. And here is the expanded versions of the both the sections. So this is aromatic, and this is aliphatic. And now let's also get to the splitting patterns here. So this is a doublet. This is a triplet of doublets. And then this is triplet. This is doublet. This one right here is a quintet. This is a triplet. This is a triplet. Now, let's go first take a look into the aliphatic region and find out what kind of hydrogens we have here. Now, the first peak right here, the one in the aphel region, is actually a quintet. When it's going to be a quintet, we can clearly see that it is going to be adjacent to 4 hydrogens. But before that, we also needed to find out what kind of hydrogens are these. For that, we have to take a look at the depth spectrum, where we can see that there are 3 CH2 peaks here. Because like whenever you have these appearing in the negative region, that's going to be corresponding to the CH2s. And I couldn't see any CH3s here, right? So therefore, we can clearly assign that these hydrogens are actually attached to the to methylene carbon. So the first CH2 is actually a quintet. If it's going to be a quintet, then we can clearly see that it is sandwiched between 2 methylene carbons. So this is my CH2, which needs to appear as the quintet. And then each of these CH2s need to be counted as well. So each of these should be a triplet. If this is going to be a triplet, then probably it's not attached to any neighboring hydrogens. So out of this, one is actually appearing in the slightly downfield, which means we can clearly see that it is going to be attached to some electron withdrawing groups. Okay, and then this is going to be in between, and then you also have another CH2. So this itself is going to count for another CH2. So in the aliphatic region, all we have is 3 CH2s. And then what we are going to do here is we are going to subtract these many carbons and hydrogens from our original molecular formula to find out what other groups are present. So let's do that now. So C10H10O minus, we have 3 carbons and then 6 hydrogens. So when we do that, when we do the subtraction, we are getting C7H10O. Now in the aromatic region, we can clearly see that there are 4 hydrogens. So 1, 2, 3, 4, because there are 4 peaks here, right? So which tells us that our aromatic ring structure is actually disubstituted. But at this point, we can easily rule out that it is not para-substituted, because the para-substituted is always going to give us 2 doublets. Okay, and we don't see 2 doublets here. It's actually a mixture of doublets and triplets. We only have 2 possibilities. One is ortho-substituted, and the other one is meta-substituted. But if it's going to be meta-substituted, then this hydrogen right here should be existing as a singlet, and we are not able to find any singlets here in the aromatic region. So we can easily assume that it is going to be ortho-substituted. Now what we are going to do is we are going to subtract the molecular formula of this di-substituted benzene from our original molecular formula, or like from the remaining molecular formula. So the di-substituted benzene is going to be C6H4. So let's subtract that. So we're going to subtract C6H4 from whatever is left behind. So that's going to leave us with a carbonyl group, okay, a C double bond O. So now let's put all of these things together. So we know that we are going to have ortho-substituted benzene, and then we have a carbonyl group, and then we also have 3 CH2s which are arranged in a row. Now let's find out how we can put all of these three fragments together. Let's take a look at the degrees of unsaturation. We have a total of 6 degrees of unsaturation. Now for the benzene ring, it's going to be 4 degrees of unsaturation, because the ring itself is going to count for 1, and then we have 3 double bonds, so that's going to be 4 degrees of unsaturation. And for the carbonyl group, it's going to be 1, so 4 plus 1, that's going to be 5. And then from the molecular form, from the degrees of unsaturation, we can easily tell, and as well as the NMR spectrum, we can clearly see that there is no double bonds or triple bonds, right? So the only way that these fragments could exist together as one structure is when there is going to be another ring. So the 6th degree of unsaturation is going to correspond to another ring. So let's see how we can put all of these 3 groups together in a ring structure, in an additional ring structure. So there is going to be a bicyclic structure, and then you have a carbonyl group, and as well as the 3 CH2 groups which are arranged together. Okay, so one possibility is where we can write, so if this is going to be ortho-substituted, so then we should have 2 groups here, and then we know that there is the 3 CH2s are arranged together, so we can put the 3 CH2s. So here are the 3 CH2s together, and then finally connected to the other carbon. We still need to find out which hydrogens are correlating with which. Let's identify some of the carbons from here. So we can clearly see that these are going to be quaternary carbons, because these carbon peaks are missing in the that spectrum. And we can assign this to be easily the carbonyl group, the carbonyl carbon, and then these two should be, the other 2 quaternary carbons are actually these without any hydrogens. So that's going to be these, like these 2 peaks should correspond to that. Okay. And we can assume that this carbon right here is going to be existing at 145-ish ppm, whereas this carbon is going to be existing about 132 ppm. Now, other than that, we also are able to see the 3 CH2s. So here are our CH2s. We can definitely assume that this carbon that's closest to the carbonyl group is definitely going to be in the outfield region. And then other than that, we also are able to see that there are 4 CH carbons, 4 methane carbons. And here are our 4 methane carbons. Okay, so these are the methane carbons, and here are our quaternary carbons, and then finally these are the CH2 carbons. Okay, now what we are going to do here is we are going to number the carbon peaks going from downfield to upfield. So 1, 2, 3, 4, 5, and there are 2 peaks here, 6, 7, 8, 9, 10. So there are totally 10 carbons, and that's exactly what we find from the molecular formula as well. So we totally have 10 carbons. Now let's take a look into the HMR spectrum and find out the correlations between the hydrogens, and then we'll come back to the depth, and we'll finally go on to HSQC. Okay, here is our COSY and HMQC. Let's first draw the structure, the proposed structure. So here is our proposed structure, and I also wanted to show the hydrogen. For now, I'm just going to show only one hydrogen, but remember each of these carbons is going to have two hydrogens. And then on the benzene ring, there is only one hydrogen. Okay. The first thing that I'm going to do here is I'm going to letter the peaks that's present in the HNMR going from downfield to upfield region. C, D, E, F, G. And then I will also mark this expanded version right here. Okay. So that's going to be this region right here, so which is my A, B, C, D. And the next thing that I'm going to do is I'm going to draw the diagonal. So it's better to use the ruler. Okay. So once I do the diagonal, I wanted to mark down the points, mark down the ppm values for the peaks even on the x-axis. So let's do that by drawing the perpendicular lines here. I'm going to take the center, the points from the central diagonal, and then go across to the x-axis. Okay, that's how best I could draw. And then what I'm going to do here is I'm going to mark the points where these peaks, A, B, C, D, E, F, G peaks are going to show up on my x-axis. So let's do that. And once I do that, I can even erase this. I don't need these lines. Okay. Let's mark these points as A to G, C, D, E, F, G. We can also work on the expanded part. Okay, so we have also done exactly the same thing where we have numbered the peaks that present even in this enlarged section. Okay, so now what we are going to do is we are going to find out all these cross peaks. So there are totally 1, 2, 3, 4, 5, 6 cross peaks, and we wanted to find out what is the correlation, what kind of correlation exists between the different hydrogens. Okay, so for that we are going to draw the perpendicular lines. Okay, and again there is correlation between E and G, and then when we go here for the aromatic region, there is correlation between B and D, and then again there is a tiny spot right there, so we should also account for that. So there is correlation between B and C. Then finally there is correlation between A and C. Okay, so it's better to write the correlations here. So this is going to be correlation between F, G. I'll be consistent. So if I choose to write the letter from the y-axis, I'll put that in the front and then followed by the letter from the x-axis. So FG, and this is correlation between EG, and then this is the correlation between B and D, and then there is correlation between B and C, and then finally this is the correlation between A proton and C protons. Okay. Okay, from the NMR spectrum we are able to identify, we previously identified that this hydrogen should be the one that needs to come in the downfield region. So basically this should be definitely E. So let's label that. So this hydrogen is going to be He. And then we wanted to find out what would be, what are the hydrogens that this is going to correlate with. So we don't have any hydrogens on this carbon. The only carbon which has hydrogens is going to be the adjacent carbon, right? So now from the COSY spectrum, we can clearly see that E is coordinating with G. So this should be G. Okay. And let's go identify this hydrogen right here. So G should correlate with E and as well as this hydrogen. So now what should be this hydrogen? We are able to see that G is correlating with F, right? So this hydrogen should be F. Now we were able to find out all of these hydrogens that's present on the methylene carbon. Let's go on to the other side. In the aromatic region, we have 4 protons. And out of this, we can clearly see that this hydrogen right here is the one that should be in the D-shielded region. Why? Because it's closer to the carbonyl group. So this should definitely be A. And also it confirms with our structure, because this one, if this hydrogen right here should be split as a doublet, okay, because there is only one neighboring hydrogen. Of course, there could be some long range coupling, but that's going to be like really fine. This is going to be our HA protons. So that's A, right? So this is going to be our HA proton. And then another hydrogen that could exhibit a doublet would be this hydrogen, because again, this is also another hydrogen which has only one neighboring hydrogen. So the only other doublet that I see here is here in the upfield region. So this should be assigned as HD. Now we only needed to assign these 2 hydrogens right here. For that, let's go take a look into the correlations. So this hydrogen needs to be correlated with A, and then similarly this hydrogen needs to be correlated with D. So let's find out. So A should correlate with this hydrogen. So when we look into this, A is correlating with C. I don't see like A is correlating with D or A is correlating with B. So definitely this hydrogen should be C. So let's mark this one now. And then what are the protons that D is correlating with? D is correlating with B. Okay. So therefore this hydrogen should be B. Now let's find out. So B and C should correlate with each other, and therefore there should be a spot that existing for it. So we can clearly see that there is correlation, there is a spot, there is a cross peak for B and C correlation, and then there should be a cross peak for B and D correlation, which we are able to see here, and there should be a cross peak for A and C. That is exactly what we see in the region. So this is going to be the interpretation for the COSY spectrum. Okay. Now that we have identified the hydrogens here, let's go to the HMQC spectrum to do exactly the same thing, to find which hydrogens are connected to which carbon. Okay. Again, I'm going to number these carbons. Okay. You have to be like a little bit careful, because right now this peak that is existing in the downfill region is at 145. But our peak from the actual C13 started at like 190. So this is going to be the first carbon, but your HMQC starts at carbon 2. So be very careful with that. So let's number these carbons. That's going to be 2, 3, 4, 5, 6, and 7. And this is going to be 8, 9, 10, and this is the solvent peak. Let's do the same thing here. Let's start from here. We are actually starting from 3 here. So this is going to be the third carbon. 3, 4, 5, 6, and 7. And let's also label the hydrogens. So that's going to be A, B, C, D, E, F, G. And then this is going to be A, B, C, D. Now all we are going to do here is we are going to just draw the perpendicular lines. So let's do it. And then for the aromatic section, let's work with this. let's mark these points. Let's give references for these points. So that's going to be G10. This is E9. And this is F8. And this one right here is C7. And this is D5. And this is A6. And this one right here is B3. Now let's also assign the carbons here. So He carbon is connected to carbon 10. So this carbon should be carbon 10. And on E, this carbon is going to be carbon 9. And then F8, so that's going to be carbon 8. And then we already know that the carbonyl carbon is going to be number 1. And then we have in the aromatic region, HD is associated with carbon 5, and HB is associated with carbon 3, and A is associated with carbon 6, and then C is associated with carbon 7. Now we are only left with carbon 2 and carbon 3, so these should be carbon 2 and 3. Out of this, carbon 2 should be the one that's existing in the downfield region. So let's find the two other quaternary carbons. So we have carbon 2 and carbon 4. So this should be carbon 2, and then finally this should be carbon 4. So now using COSY spectrum HSQC or HMQC, we are now able to assign the hydrogens and as well as carbons, and are also able to find the correlations between them.